Hello there, and welcome to Sleepy Science Vault. Somewhere out there, roughly 600 million kilometers from where you are sitting right now, a planet larger than all the others combined is quietly holding an entire solar system together. Tonight, we are going to ask a question that sounds simple at first, but grows stranger and more beautiful the longer you sit with it. What if Jupiter had never existed? Not destroyed. Not exploded. Simply absent. As if the swirling disk of gas and dust that gave birth to our sun and planets had, for some reason, never gathered enough material in that one particular region of space to form a giant. It is a quiet kind of thought experiment. No explosions, no chaos to imagine, at least not at first. Just an empty space where something enormous used to be. And from that simple absence, an entire chain of consequences begins to unfold, stretching backward into the earliest days of our solar system, and forward into the stable, orbiting world we know today. So settle in. Let your mind drift toward the outer solar system, toward the space beyond Mars, toward that vast gap where a giant planet has spent over 4.5 billion years shaping everything around it. Tonight, we explore what would happen, and what would not happen, if Jupiter simply was not there. Let's begin with something surprisingly practical. Something almost mundane, in the best possible way. If Jupiter vanished this very instant, right now, while you are listening to this, you would not know. Not immediately. Not for a while, actually. Some estimates suggest it would take about 32.6 minutes before we noticed anything had changed at all. Why? Because light itself needs time to travel. Jupiter sits so far from Earth that the sunlight reflecting off its clouds, the glow we see when we look up at that bright wandering star in our night sky, takes over half an hour to reach our eyes. So even in this imagined scenario, even if Jupiter blinked out of existence in a single moment, the universe would not immediately reveal that secret to us. For 32 minutes, we would still be looking at a ghost. A version of Jupiter that, technically, no longer exists, but whose light is still finishing its long journey across the dark. There is something quietly humbling about that. It reminds us that when we look at the night sky, we are never really looking at the present moment. We are looking backward in time. Layers upon layers of old light, arriving late, telling us stories about a past that has already moved on without us. And this leads naturally into our second fact, because even after that half hour passed, even after the light finally faded, the rest of the solar system would not suddenly fall into chaos. Not immediately, anyway. The sun is, and has always been, the dominant force holding our planetary system together. It contains about 99.8% of all the mass in the entire solar system. Everything else, all the planets, moons, asteroids, comets, combined, is little more than a rounding error next to that. So even without Jupiter, the sun's gravity alone would continue to hold Earth, Mars, Venus, Saturn, and the rest, in roughly their expected orbits, at least in the short term. There would be no sudden planetary pandemonium. No dramatic collisions in the days or months following Jupiter's disappearance. Life, quite strangely, would go on largely as normal, for a while. but for a while is doing a lot of quiet work in that sentence. Because here is where the story deepens. Jupiter may be small compared to the Sun, but compared to every other planet, it is a giant beyond comprehension. It holds more mass than all the remaining planets in our solar system combined. Saturn, Uranus, Neptune, Earth, Venus, Mars, Mercury, all of them together, and Jupiter would still outweigh them. That kind of mass does not simply sit quietly in space. It reaches outward with its gravity, tugging gently, or sometimes not so gently, on everything around it. Over long stretches of time, thousands, and hundreds of thousands, and millions of years, that gravitational influence subtly reshapes orbits. It nudges asteroids. It flings comets. It stabilizes, or destabilizes, entire regions of the solar system. So while removing Jupiter would not cause instant disaster, it would slowly, gradually, patiently unravel a certain kind of balance. A balance that took billions of years to settle into place. And this brings us to a strange kind of paradox, one worth sitting with for a moment. Jupiter accounts for only a small fraction of the Sun's total mass, yet without Jupiter, the overall mass distribution of the solar system would shift in a meaningful way. Not enough to break anything suddenly, but enough to matter over deep time. Enough to change the story of how everything moves, how everything settles, how everything eventually finds its place. It is a bit like removing one particular stone from a very old, very carefully balanced arch. The arch does not collapse the instant the stone is gone, but the structure is no longer quite the same. The way weight travels through it has changed. And eventually, given enough time, that difference reveals itself. Now let us travel back. Back beyond the stable solar system we know today. Back to its chaotic infancy, billions of years ago, when everything was still forming. In our real history, the early solar system was a place of extraordinary turbulence. Countless pieces of rock and ice, drifting, colliding, merging, breaking apart again. Slowly, out of that swirling chaos, planets began to take shape. Jupiter, in our timeline, played an enormous role in calming some of that chaos. Its gravity helped clear away debris, fling wandering material into new orbits, or eject it from the solar system entirely. In a strange way, Jupiter acted like an early gravitational shepherd, guiding loose material into more predictable, more stable paths. Without Jupiter, that early solar system would likely have remained more chaotic for longer. More debris left lingering on unstable paths. More unpredictable interactions between forming worlds. The quiet, orderly solar system we know now might have taken a very different, and possibly much longer, road to reach any kind of stability. It is worth pausing here, just for a moment, to imagine that version of history. A version where the early solar system stayed wild for longer. Where the gentle order we now take for granted was never guaranteed, but rather something hard-won, shaped in part by one enormous planet quietly doing its gravitational work in the dark. And this connects to something else, something a little more structural in how we understand the solar system's formation. Scientists often think of planet formation as if it happened in two separate stories, an inner solar system story, close to the Sun, where small rocky planets formed, and an outer solar system story, farther out, where gas giants took shape. But Jupiter's early history complicates that clean separation. Jupiter's formation timeline appears to link these two regions together into a single, connected evolutionary story, rather than two isolated ones happening independently. The timing of Jupiter's growth, the way it moved, the way its gravity interacted with the surrounding disk of gas and dust, all of that likely influenced conditions much closer to the Sun, shaping how and when the rocky planets like Earth and Mars came together. In other words, Jupiter was not simply a distant giant, minding its own business far from the inner planets. It was, in a very real sense, part of the story of how Earth itself came to be. Which means, in a universe without Jupiter, that story might have unfolded very differently indeed. Let's linger on that formation process a little longer, because it is genuinely fascinating. In the world we actually live in, both Jupiter and Saturn are thought to have formed through a similar process. Large solid cores gradually built up first, gathering rock and ice across the early disk surrounding the young Sun. Once those cores grew large enough, they began pulling in enormous amounts of surrounding gas, rapidly swelling into the gas giants we recognize today. But this could only happen while the surrounding nebula, the vast cloud of gas left over from the Sun's own formation, was still present. That gas does not last forever. Eventually, it dissipates, blown away by radiation and stellar wind, or simply drawn into the Sun itself, or scattered into interstellar space. If Jupiter had never formed, it likely means that, for whatever reason, a large enough core never came together quickly enough, in that particular region of space, before the surrounding gas disappeared. A narrow window missed. And if that window closed differently, the entire architecture of planet building in the outer solar system could have unfolded along a completely different path. Which brings us, quite naturally, to Jupiter's gravitational neighbors: Saturn, Uranus, Neptune. These giant worlds did not form in isolation. Their positions, their spacing, even their orbital rhythms today, were shaped in part by their gravitational relationship with Jupiter. Some models even suggest that in the early solar system, these outer planets migrated, drifting inward or outward from where they first formed, partly guided by gravitational interactions with each other, and especially with Jupiter. Without Jupiter's presence, without its immense gravity threading through the outer solar system like a kind of cosmic architecture, Saturn, Uranus, and Neptune could easily have ended up arranged quite differently. Perhaps closer together. Perhaps farther apart. Perhaps in a completely different order altogether. It is a strange thing to consider, that the outer solar system's layout, something that feels so fixed, so permanent, so simply the way things are, might actually be the result of one giant planet's particular gravitational influence, at one particular moment in history. And this leads us towards something even bigger, a thought that stretches beyond our own solar system entirely. When astronomers study other star systems, they often find planetary arrangements that look nothing like ours. Giant planets sitting extremely close to their stars. Multiple large worlds crowded together in tight formations. Systems that seem, in many ways, more common across the galaxy than our own particular arrangement. Some simulations suggest that our solar system's structure, the way Jupiter and Saturn grew, moved, and settled into their current positions, may represent a fairly specific and possibly uncommon sequence of events. Not impossible elsewhere, but perhaps not the default outcome either. Which means, our version of the solar system, calm, spaced out, seemingly orderly, might be something closer to a fortunate exception, rather than a predictable rule. And that brings us to where we will pause, for now, in this first chapter of our story. Because if there is one central idea worth carrying with you into the quiet hours ahead, it is this. A solar system without Jupiter would not simply be a slightly less protected version of the one we know. It would not just be our solar system, minus one planet. It would likely be an entirely different formation story altogether. Different spacing between the outer planets. Different distribution of ancient debris. A different rhythm to those earliest, most chaotic years, when the solar system was still finding its shape. Jupiter, it turns out, is not simply a giant sitting quietly in the outer dark. It is woven into the very story of how everything else came to be exactly where it is. And in our next chapter, we will follow that story even further. Into the asteroid belt. Into the debate over whether Jupiter truly acts as Earth's cosmic protector. Into questions that scientists are still, even now, quietly trying to answer. For now, let this first set of ideas settle gently in your mind, as we drift onward, together, into the deeper mysteries of a solar system shaped by a giant that might, in some other universe, never have existed at all. You may remember, from our last chapter, the strange idea of Jupiter as an invisible architect, quietly shaping the outer solar system long before Earth ever existed. Now we turn our attention closer to home. Because Jupiter's influence did not stop at the outer planets. It reached inward, toward the very region where our own world was forming. There is a theory among scientists that Jupiter did not simply form in one place and stay there. Instead, in its early life, Jupiter may have wandered. It is thought to have migrated inward, drifting closer to the Sun than it sits today, before eventually reversing course and drifting back outward to something closer to its current position. This idea carries a rather poetic name in astronomy circles. Some call it the Grand Tack, as if Jupiter, like a great sailing ship, tacked inward against the wind of the early solar system, only to turn and sail back out again. This wandering was not a gentle stroll. Jupiter is an immense body, and as it moved, its gravity dragged and disturbed the material around it. Anything in its path, gas, dust, small rocky bodies just beginning to clump together, would have felt the pull of that passage. And this single, quiet migration may have completely reshaped where and how the inner planets, including our own Earth, eventually came together. Picture the inner solar system in its earliest days. A wide, dense disk of gas and dust, swirling gently around the young sun, countless small bodies drifting through it, some no larger than pebbles, others already growing into what scientists call planetary embryos, small rocky worlds still gathering mass. This was the raw material from which Mercury, Venus, Earth, and Mars would eventually be built. Now imagine Jupiter moving through that region, not once, but twice. First inward, then back out again. As Jupiter passed through, its gravity would have scattered much of that material. Some of it flung outward into more distant orbits. Some pulled inward, closer to the Sun. Some simply thrown into unstable paths where it eventually spiraled inward and was lost, swallowed by our star entirely. In effect, Jupiter's passage acted like a kind of cosmic broom, sweeping through the inner solar system and clearing away much of the material that had originally gathered there. This is a fascinating consequence, one that helps explain something scientists have long puzzled over. When we look at our inner planets today, Mercury, Venus, Earth, and Mars, we notice something curious. They are relatively small and low in mass, especially when compared to some of the rocky super-Earths astronomers have discovered orbiting other stars. For a long time, this seemed like a mystery. Why did our inner solar system produce such modest, relatively lightweight planets, when other star systems seem to build much larger rocky worlds so easily? Jupiter's early migration may hold part of the answer. By sweeping through the inner disk and clearing away a significant portion of the original planet-forming material, Jupiter effectively limited how much raw material remained available to build Mercury, Venus, Earth, and Mars. It was not simply that the material was already limited to begin with. It was actively reduced, reshaped, redistributed by Jupiter's passage. So in a strange and rather humbling way, Earth's own modest size may be partly a gift, or perhaps a side effect, of a giant planet's ancient wandering. And this brings us to a truly fascinating question. What if that wandering had never happened at all? What if Jupiter had simply stayed farther out, and never migrated inward in the first place? In that alternate version of history, the inner solar system would never have experienced that great clearing event. The material that Jupiter's migration scattered, or drew inward, or ejected entirely, would instead have remained in place. Denser. More crowded. A much richer reservoir of planet-building material left largely undisturbed. From that untouched, more abundant environment, the inner planets may have formed quite differently. Perhaps larger. Perhaps more numerous. Perhaps arranged in an entirely different pattern than the four rocky worlds we know today. Instead of the relatively clean, orderly inner solar system we inhabit, shaped by Jupiter's ancient passage like a sculptor's careful strokes, we might have inherited something far more crowded. A more chaotic construction site, filled with additional planetary embryos all competing for the same limited space, all pulling at each other's orbits, potentially colliding, merging, and reshaping one another over long stretches of time. It's worth sitting with that thought for a moment. The Earth we know, calm and singular in its orbit, may exist in its particular form precisely because Jupiter once passed through the inner solar system like a slow, patient tide, quietly rearranging everything in its wake. Let us now shift our attention to something smaller in scale, but no less important, the individual pebbles and grains of dust drifting through that early protoplanetary disk. It is easy to imagine planet formation as simply large chunks of rock slowly colliding and sticking together. But in reality, much of the earliest stages of planet building happen on a much smaller scale, through what scientists call pebble accretion. tiny particles of dust and ice, drifting through the gas-rich disk, gradually clumping together, forming slightly larger pebbles, which then continued to gather more material, slowly growing into planetary embryos. This process depended heavily on how those pebbles moved through the disk, how freely they drifted, where they tended to gather, and how quickly they could grow. Jupiter's early presence, simply by existing as a massive body embedded within that disk, altered this pebble flow significantly. Its gravity influenced the movement of gas around it, which in turn influenced how pebbles drifted, where they slowed down, and where they tended to accumulate. In some regions, Jupiter's presence may have sped up planet formation, concentrating material more efficiently. In other regions, it may have disrupted the process entirely, scattering material before it had a chance to properly gather. This is a subtle but important shift in how we think about early planet formation. Jupiter was not simply a large body forming somewhere out in the disk, indifferent to its surroundings. It was an active participant, continuously reshaping the very river of material from which every other planet, including Earth, would eventually be built. To understand this more clearly, imagine that protoplanetary disk not as a still, quiet cloud, but as something closer to a great flowing river of gas and dust, all gently spiraling inward toward the young sun. Now imagine placing a massive boulder directly in the middle of that river. That is, in essence, what Jupiter's formation did to the flow of material around it. As Jupiter grew, it began carving a path through the surrounding disk, disturbing the smooth, steady flow of gas and dust. This created ripples, disturbances that spread outward from Jupiter's position like waves. And just as a large rock in a river creates turbulence and eddies downstream, Jupiter's gravitational disturbances created something similar within the disk. Regions where material slowed down, bunched up, or became temporarily trapped. Scientists sometimes describe these disturbances using a very relatable metaphor: traffic jams. Just as cars on a highway slow down and cluster together when there's an obstruction ahead, streams of dust and gas within the disk would slow and accumulate wherever Jupiter's gravity created resistance. And these traffic jams were not simply random disruptions. They had consequences. In regions where material became trapped or slowed by Jupiter's gravitational influence, dust and small particles had more time and opportunity to collide, stick together, and grow. Rather than continuing to drift steadily inward toward the sun, this gathered material had a chance to settle, concentrate, and build upon itself. In other words, these localized traffic jams created by Jupiter's presence may have become natural nurseries for planet formation. Places where the conditions were just right for loose material to begin transforming into something more solid, more structured, the very earliest seeds of planets or planetary building blocks. This idea connects to something scientists call pressure bumps within the protoplanetary disk. As Jupiter grew large enough, it began to carve out a partial gap in the surrounding gas, a region where its gravity pulled material away, creating a kind of groove within the disk. Along the edges of these gaps, gas pressure could rise unevenly, creating what astronomers call pressure bumps, localized regions where the balance of forces acting on dust particles shifted just enough to slow their inward drift. Rather than continuing to spiral steadily toward the sun, dust particles passing through these pressure bumps would slow down and begin to accumulate, much like leaves gathering along the edge of a slow-moving stream. Over time, this accumulation could become significant enough to encourage the formation of new solid bodies, small planetesimals, the very early building blocks of planets. So once again, we find these pressure bumps behaving much like the traffic jams we described earlier, regions where material naturally gathered and slowed, rather than continuing to drift freely inward. And what is especially remarkable here is that Jupiter's own rapid growth appears to have been directly responsible for creating these conditions. As Jupiter carved its gap within the surrounding gas, it inadvertently created the very pressure bumps that allowed dust to collect and new solid material to begin forming elsewhere in the disk. There is something quietly beautiful in this idea. Jupiter, simply by growing into the massive planet it became, reorganized the entire flow of material around it, creating quiet gathering points, gentle traffic jams and slow currents, where new worlds could begin to take shape. It reminds us that planet formation was never simply a story of matter randomly colliding by chance. It was a much more intricate, interconnected process. One where the presence of a single, enormous planet could ripple outward, influencing conditions across vast regions of the forming solar system, shaping not just its own growth, but the very possibility of other worlds forming nearby. And so, as we drift toward the end of this second chapter in our story, let us hold on to this deepening picture. The solar system we know today, its planets, their sizes, their spacing, their compositions, was never simply the result of separate, isolated events happening independently of one another. It was, instead, one long, continuous, deeply interconnected process. A process in which Jupiter, quietly, patiently, and often invisibly, played a defining role from the very beginning. In our next chapter, we will continue following this thread, moving even deeper into the intricate relationship between Jupiter and the formation of the world we now call home, uncovering still more ways that one giant planet's early history may have shaped the quiet, stable solar system we find ourselves living in today. For now, let this gentle picture settle in your mind, of pebbles gathering in slow cosmic traffic jams, of pressure bumps quietly cradling the seeds of new worlds, as we continue drifting, together, through the deep and patient story of how our solar system came to be. We left our story last time with a quiet image, of dust and pebbles gathering in slow cosmic traffic jams, trapped along invisible pressure bumps within the swirling disk that once surrounded our young Sunday. Now, let us follow that image a little further. Because those traffic jams were not simply isolated pockets of gathered material, scattered here and there without pattern. They may have formed something far more structured. Something that, remarkably, we can still observe happening in other star systems today. When astronomers point their most powerful telescopes toward young, still-forming planetary systems, distant stars only a few million years old, they sometimes see something striking. The disks of gas and dust surrounding these young stars are not smooth and uniform. Instead, they often display beautiful, concentric rings. Bright bands separated by darker gaps, almost like the rings of Saturn, but on a much faster scale, stretching across the entire forming solar system. For a long time, scientists wondered what could cause such intricate structures to form. And Jupiter, it turns out, may offer part of the answer. As Jupiter grew rapidly in our own early solar system, it likely did more than simply carve a single gap in the surrounding disk. Its powerful gravity may have created a whole series of rings and dust traps radiating outward from its position. Distinct regions where material gathered, separated by emptier gaps where Jupiter's gravitational influence had cleared much of the material away. Within these ring-like structures, dust and pebbles that had been trapped and concentrated could continue colliding and merging, slowly building into a second generation of planetesimals. Not the very first solid bodies to form in the solar system, but a later wave, shaped directly by the changes Jupiter had already introduced into the disk. There is something quietly fascinating in this idea, that Jupiter's growth did not simply happen once and then stop. It set into motion an ongoing structuring process. One ring after another, one generation of forming bodies after another, all shaped by the presence of this one enormous planet slowly settling into its place in the outer solar system. And what makes this even more compelling is that we are not simply imagining this process based on our own solar system alone. We can now see similar ring structures forming around other young stars scattered throughout the galaxy. When we look at these distant, newly forming planetary systems, glowing softly in infrared light, we often find those same concentric rings and gaps, echoing the very structures scientists believe Jupiter once created in our own early disk. This gives researchers a rare opportunity, a chance to study, in real time, processes that happened in our own solar system billions of years ago, but that are still actively unfolding elsewhere in the galaxy today. These observations strongly suggest that Jupiter's early growth was not some unusual, one-time event unique to our particular corner of the galaxy. Rather, it reflects a broader pattern. Wherever a planet grows massive enough, quickly enough, within a young protoplanetary disk, it appears capable of reshaping the entire structure of that disk. Carving rings, creating gaps, organizing scattered material into distinct bands. In other words, watching these distant systems form gives us a kind of mirror, a reflection of our own solar system's ancient past, still playing out, quietly and patiently, around other stars. Now, let us turn back toward home, and consider something particularly important for the story of Earth itself. We often think of planet formation as new material simply gathering together and growing larger over time. But there is another force at work in these early disks, one that can just as easily undo that growth. Migration. The slow, gravitational drift of forming planets and planetary embryos inward, toward the Sun. In these young systems, interactions between a forming planet and the surrounding gas disk can create something called migration torques, gentle gravitational forces that gradually push a forming planet inward, sometimes causing it to spiral closer and closer to its star over time. In many other planetary systems observed across the galaxy, we see clear evidence of this happening. Giant planets discovered sitting remarkably close to their host stars, in orbits far tighter than anything we see among our own planets. This raises an intriguing question for our own solar system's history. What kept our inner planets, the small rocky embryos that eventually became Mercury, Venus, Earth, and Mars from experiencing that same fate? What prevented them from simply spiraling inward, ultimately falling into the sun during those early, turbulent years? Once again, Jupiter's early influence may hold part of the answer. As Jupiter grew large enough to carve its own gap within the surrounding gas disk, it likely disrupted the smooth flow of gas that would otherwise have continued moving steadily inward, past its orbit, toward the inner solar system. By interrupting that flow, Jupiter may have effectively reduced the strength of the very migration torques that could have otherwise pulled the young terrestrial embryos inward. In simpler terms, Jupiter's presence may have acted almost like a gentle brake. Or perhaps more precisely, a gravitational stall point. A place where the smooth inward pull that so often drags young planets toward their star was interrupted, weakened, disturbed just enough to allow the forming rocky worlds behind it, closer to the Sun, to stabilize in place rather than continuing to spiral inward. This idea offers a striking possibility. That the very fact Earth still orbits where it does today, rather than having spiraled inward billions of years ago and been lost to the Sun entirely, may be connected, at least in part, to Jupiter's early presence quietly disrupting the gas flow further out in the disk. And if Jupiter had never existed, this protective stalling effect may never have occurred at all. Without Jupiter's gap-opening influence, the flow of gas through the inner disk may have remained smooth and largely uninterrupted. Migration torques acting on the young terrestrial embryos, the earliest building blocks of Earth and Venus, could have remained strong and largely unchecked throughout that critical early period. In such a scenario, some models suggest these growing rocky embryos may have spiraled inward far more rapidly than they did in our actual history. Rather than settling into stable, long-lasting orbits, drifting instead toward the Sun, potentially merging together chaotically along the way, or in the more extreme cases, eventually being consumed by the Sun entirely before ever reaching anything resembling the mature planets we know today. It's a striking thought, to imagine a version of history where Earth's own rocky ancestors, those early planetary embryos slowly gathering mass in the young disk, never had the chance to settle into a stable orbit at all. Where the raw material that eventually became our home world was instead drawn ever closer to the Sun, lost long before life, or oceans, or even a solid, stable surface, had any chance to form. Now, it's worth remembering something important here. Jupiter, in its earliest days, was not quite the planet we observe today. Some models suggest that during this critical early period, Jupiter may have been considerably larger than its current size, potentially close to twice its eventual mass, before later losing material and settling into the more familiar giant we recognize now. This detail matters a great deal, because it means Jupiter's early gravitational influence, its ability to disrupt gas flow, carve gaps, create pressure bumps and rings, and interrupt migration torques, may have been considerably stronger during this formative period than we might otherwise expect based on its present-day size alone. In other words, the young Jupiter, still growing, still settling into its final form, may have wielded even greater influence over the shape of the early solar system than the mature Jupiter we see quietly orbiting the Sun today. And this brings us to one final, particularly delicate thread in this part of our story. Beyond simply influencing where and how planets formed, or whether they drifted inward toward the Sun, Jupiter's early presence may have also played a subtler, more chemical role. One connected to the very ingredients from which our solar system's planets were built. The outer regions of the early solar system, far from the Sun, likely contained different chemical materials compared to the warmer, inner regions closer to where Earth would eventually form. Certain volatile compounds, various types of ice, and specific isotopic signatures tend to concentrate more heavily in these colder, outer reservoirs. Normally, over time, pebbles and small particles from these distant, chemically distinct regions might gradually drift inward, gently mixing with material from the inner disk. But Jupiter's early growth may have interrupted this process as well. As Jupiter's growing gravity created its now familiar gap within the disk, it likely also created what scientists sometimes call a pebble isolation effect. Essentially, a kind of gravitational barrier, preventing pebbles from the outer disk from continuing their inward drift past Jupiter's orbit. By blocking this pathway, Jupiter effectively limited how much mixing occurred between these two chemically distinct regions, the colder, more volatile rich material from the outer solar system, and the warmer, drier material closer to the Sun. Had Jupiter never existed, this particular isolation effect may never have occurred at all. Without Jupiter's gap acting as a kind of quiet gatekeeper, material from the outer disk may have continued drifting inward largely unimpeded, gradually blending with material closer to the Sun over a much longer period of time. In such a scenario, the chemical makeup of the inner planets, including Earth, may have looked noticeably different. Perhaps richer in certain volatile compounds. Perhaps carrying a different isotopic fingerprint than the one we actually observe in rocks and meteorites here on Earth today. It's a delicate, almost invisible kind of influence. Not something we can see directly in the sky, or trace through orbital patterns alone. But something scientists can still detect, quietly encoded within the chemistry of ancient meteorites and the rocks beneath our feet, faint clues pointing back toward a Jupiter that, once again, appears to have shaped far more of our solar system's story than its size or distance might first suggest. As we begin drawing this third chapter to a close, it's worth pausing to notice just how many threads we have now gathered together. Rings and dust traps, echoed in the disks of distant young stars. Gas flow interrupted, quietly protecting the fragile orbits of our inner planets. And chemical boundaries, drawn invisibly across the early disk, shaping the very composition of the world we now call home. None of these processes happen in isolation. Each one connects back to the same enormous, quietly influential presence. Jupiter, forming and growing in the outer solar system, its gravity rippling outward and inward in ways that touched nearly every corner of our early planetary system. In our next chapter, we will continue following this deep, interconnected story even further, exploring still more ways that Jupiter's ancient presence may have shaped the delicate, complex history of our solar system, and the quiet, stable world we now call home. For now, let this picture settle gently in your mind, rings within rings, quiet gatekeepers at the edge of a young solar system, and the slow, patient chemistry of a home world still waiting, patiently, to be born, as we continue drifting, together, deeper into this long and remarkable story. We paused, in our last chapter, at the edge of something quietly delicate. A chemical boundary, drawn invisibly across the early solar system, separating the volatile rich material of the outer disk from the warmer, drier material closer to home. Now, let us follow that boundary a little further. Because if Jupiter had never existed, that boundary may never have formed at all. Think back to the picture we built earlier, of Jupiter carving a gap within the surrounding gas disk, creating what scientists call a pebble isolation effect. A kind of gravitational checkpoint, holding back much of the solid material drifting inward from the colder, outer regions of the solar system. Without Jupiter standing in that particular place, at that particular time, this barrier simply would not have existed. And the consequences of its absence would have rippled inward, touching the very foundation of how our rocky planets came to be. In our actual history, the inner solar system developed largely from a fairly contained reservoir of material. A relatively narrow band of dust, pebbles, and small planetesimals, orbiting close to the young Sun, gradually gathering together to form Mercury, Venus, Earth, and Mars. Jupiter's presence, far out at the edge of this inner region, helped keep that reservoir somewhat isolated, limiting how much additional material could drift in from farther out. But imagine, for a moment, a version of the solar system where Jupiter never grew large enough to create that barrier, where no gap ever opened in the gas disk to interrupt the steady inward flow of solid material. In that scenario, planetesimals forming within the region that would eventually become Earth's orbit might not have grown from that same relatively limited, recycled inventory of nearby material. Instead, they may have continued receiving a steady supply of additional solid material, drifting in from much farther out in the disk. A broader, more varied mixture, arriving from far beyond where Jupiter's gap would otherwise have formed. This is a subtle but important distinction. It is not simply a question of whether more or less material was available. It is a question of where that material originally came from, which regions of the early solar system ultimately contributed their raw ingredients to the formation of our rocky planets. In other words, the very existence of a growing proto-Jupiter, even before it fully matured into the giant planet we recognize today, may have quietly redirected which specific regions of the solar system ultimately supplied the building blocks for Venus, Earth, and Mars. This connects to something scientists consider particularly important when trying to understand why our inner planets ended up with the particular sizes we observe today. For the terrestrial planets to form with roughly their current masses, especially Earth and Venus, the process seems to depend on the inner disk remaining relatively narrow and contained, rather than spreading out over a much wider region with material continuously flowing in from farther out. Jupiter's early influence appears to have helped preserve exactly this kind of narrow, contained inner disk. By limiting how much additional material could drift inward from beyond its orbit, Jupiter effectively helped concentrate the available planet-building material within a more confined region close to the Sun. This concentration, in turn, allowed Venus and Earth to grow to roughly the masses we observe today, without either becoming significantly larger or significantly smaller than they actually are. Without Jupiter's early influence helping maintain that narrower disk, our inner planets may have formed under quite different conditions, potentially leading to a noticeably different balance of sizes among Mercury, Venus, Earth, and Mars. And this brings us, quite naturally, to one of the more curious puzzles in our own solar system. Why is Mars so much smaller than Earth? Given their relatively similar distances from the Sun, at least on a cosmic scale, one might expect Mars to have grown to a size somewhat closer to Earth's. Yet Mars ended up considerably smaller, roughly 1/10 of Earth's mass. For a long time, this size difference puzzled scientists trying to model the solar system's formation. Jupiter and Saturn's early migration history may offer part of the explanation. According to certain models, sometimes referred to as the Grand Tack, which we touched on briefly earlier in our story, Jupiter and Saturn's inward and outward migration did more than simply disturb the region closer to the Sun. It may have effectively truncated the outer edge of the planetesimal disk from which the terrestrial planets formed, cutting it off at a distance roughly corresponding to where Mars orbits today, around 1.5 astronomical units from the Sun. In simpler terms, Jupiter and Saturn's migration may have acted almost like a boundary line, limiting how much planet-building material remained available beyond a certain distance from the Sun. Earth, forming closer in, had access to a richer, more concentrated supply of material. Mars, forming farther out, near the edge of that truncated region, was left with considerably less to work with. This single dynamic, Jupiter and Saturn's early gravitational dance, briefly pulling closer to the Sun before retreating back outward, may have directly shaped the present-day mass difference we observe between Earth and Mars. This process becomes even clearer when we consider a phenomenon scientists sometimes describe as chaotic excitation. As Jupiter and Saturn moved through their early migration, their combined gravitational influence likely stirred up the surrounding disk quite significantly. Rather than smoothly and gradually shaping the region where the terrestrial planets formed, their movement may have introduced genuine turbulence and instability, particularly in the outer portions of that inner disk. This chaotic stirring appears to have played an important role in narrowing the region where stable, long-lasting terrestrial planets could ultimately form. Material closer to the Sun, within roughly Earth's orbit, remained relatively protected and continued accumulating steadily. But material farther out, beyond about 1.5 astronomical units, found itself increasingly disturbed, scattered, and ultimately depleted, over a period of roughly 5 to 10 million years. This depletion appears to correspond quite closely with the region where Mars eventually formed, potentially explaining, at least in part, why Mars ended up so much smaller than its inner neighbor. Adding another layer to this picture, some models suggest that Jupiter and Saturn's early orbits may not have been as smooth and circular as we observe today. Instead, during this particularly turbulent period, both giant planets may have followed considerably more eccentric, elongated paths around the Sun. These more eccentric early orbits would have amplified their gravitational influence even further, particularly in the region beyond about 1.5 to 2 astronomical units from the Sun. This stronger, more disruptive influence may have depleted planet-forming material in that region even more significantly than a simple circular orbit would have allowed. In other words, it was not simply Jupiter and Saturn's presence alone that shaped this part of the story, but the specific, dynamic, sometimes turbulent nature of their early orbital paths. Now, let us return once more to our central question. What if Jupiter had never existed at all? Without Jupiter's gravitational influence quietly shaping and constraining the inner disk, the entire dynamic we have just described, migration, chaotic excitation, truncation of the outer planetesimal disk, would simply never have occurred. There would have been no gravitational boundary drawn near Mars's orbit. No significant depletion of material in that region. Instead, planet-forming material may have remained abundant across a much wider stretch of the inner solar system, extending well beyond where Mars currently orbits. In such a scenario, the odds of forming considerably larger rocky planets, closer to the Sun, may have increased significantly. Rather than the specific arrangement we see today, for relatively modest rocky worlds, Mercury, Venus, Earth, and Mars, our solar system might instead have developed one or more substantially larger rocky planets. Perhaps something resembling what astronomers now call super-Earths, planets often several times more massive than our own, which have been discovered quite commonly orbiting other stars throughout the galaxy. This possibility connects to something increasingly appreciated in modern astronomy. When astronomers study other planetary systems across the galaxy, they frequently observe an abundance of super-Earths, rocky planets noticeably larger than our own, often orbiting relatively close to their host stars. Our own solar system, by comparison, appears somewhat unusual. Lacking any planet of intermediate size between Earth and the much larger gas giants like Neptune and Uranus. Jupiter's early formation, and its subsequent gravitational influence on the inner disk, may help explain this apparent peculiarity. By limiting the available material and constraining the region where terrestrial planets could grow, Jupiter may have effectively prevented our solar system from developing the kind of super-Earths so commonly observed elsewhere. Without Jupiter's early presence, our solar system's inner planets may have looked considerably more similar to many of the exoplanet systems we now observe scattered throughout the galaxy, rather than standing out as a comparatively unusual, quieter arrangement of smaller rocky worlds. As we bring this fourth chapter to a gentle close, it's worth reflecting on just how deeply interconnected this story continues to reveal itself to be. From the size of Mars, to the very absence of super-Earths in our solar system, so much appears to trace back to Jupiter's early formation, its migration, and its quiet, persistent influence over the flow of material throughout the young solar system. In our next chapter, we will continue this journey, moving even further into the delicate balance Jupiter helped create, exploring still more ways that a solar system without this giant planet may have unfolded along an entirely different path. For now, let this picture rest quietly in your mind. A narrow, carefully shaped inner disk. A boundary drawn gently near the orbit of Mars. And a solar system that, thanks to one giant planet's ancient influence, ended up looking quieter, smaller, and perhaps more rare than so many of the star systems now scattered across our galaxy. We ended our last chapter with a striking thought, that the very absence of super-Earths in our solar system may itself be a kind of fingerprint, left behind by Jupiter's ancient influence. Let us stay with that thought a little longer, because it opens into an even wider question. Not just about the size of our planets, but about the entire architecture of the solar system we call home. Across the galaxy, in system after system that astronomers have cataloged, a particular pattern keeps appearing. Large rocky planets, often several times the mass of Earth, orbiting remarkably close to their host stars. Tightly packed, often several such worlds crowded into orbits far smaller than Mercury's own path around our Sun. This configuration, dominated by close-in super-Earths, seems to be one of the most common outcomes of planet formation throughout the galaxy. Our own solar system stands apart from this pattern, and Jupiter's presence may be a significant reason why. By forming early, and by shaping the inner disk in the ways we've already explored, limiting available material, truncating the planetesimal disk near where Mars orbits today, creating that narrow, contained region for terrestrial planet formation, Jupiter may have effectively steered our solar system away from the more common outcomes seen elsewhere. Rather than a crowded arrangement of large, close-in rocky worlds, we ended up with something quieter. For smaller terrestrial planets, spaced comfortably apart, none of them crowding too closely against the Sun or against each other. It's a strange thing to consider, that the emptiness between our planets, the calm, spacious quality of our inner solar system, so different from the tightly packed systems we observe elsewhere, may itself be a direct consequence of Jupiter's early gravitational influence. Without Jupiter, this particular calm may never have come to be. This leads us to something scientists sometimes describe when discussing the full architecture of the inner solar system. Not simply the existence of 4 terrestrial planets, but the very specific combination we observe today. Mercury small and close to the Sun, Venus and Earth similar in size, spaced comfortably apart. Mars smaller still, marking the outer edge of this terrestrial family. This particular combination, this exact pattern of sizes and spacing, appears to depend quite sensitively on the specific sequence of events that unfolded during the solar system's earliest history. Jupiter's formation, its possible migration, its influence on the surrounding disk. Change any one of these early conditions, and the resulting combination of terrestrial planets could easily have looked quite different. Without Jupiter, it's not simply that we might have ended up with a slightly larger or slightly smaller version of the same 4 planets. The entire combination itself, the number of terrestrial planets, their relative sizes, their spacing from one another, might have unfolded along a completely different path. Now, let us turn towards something a little more delicate. Something written not in the size or position of planets, but in their very chemistry. When scientists study meteorites, ancient fragments of material left over from the solar system's earliest history, they often analyze the specific ratios of different chemical elements contained within them. One such ratio involves phosphorus and nitrogen, 2 elements that played important roles in the young solar system's chemistry. Interestingly, meteorites originating from the inner solar system tend to show a noticeably different phosphorus to nitrogen ratio compared to meteorites originating from farther out. This chemical distinction offers scientists valuable clues about how material was distributed, and how thoroughly it mixed, during the earliest stages of planet formation. Jupiter's early growth appears to have played a meaningful role in shaping this particular chemical divide. By influencing how material moved, or in many cases, failed to move, between the inner and outer regions of the disk, Jupiter's presence likely helped preserve distinct chemical signatures in each region, signatures we can still detect today, quietly encoded within ancient meteorites. This connects to a broader and rather elegant idea that scientists have developed to help explain some of the deeper chemical patterns we observe throughout the solar system. When researchers examine meteorites in even greater detail, they find they largely fall into two distinct chemical families. One group, referred to as non-carbonaceous meteorites, tends to share certain isotopic characteristics associated with the inner solar system. The other group, known as carbonaceous meteorites, tends to share a different set of isotopic characteristics, more commonly associated with material originating farther out, beyond where Jupiter orbits today. What makes this particularly interesting is that these two chemical families remain remarkably distinct from one another, even billions of years later. There is surprisingly little chemical blending between them. For scientists, this raises an important question. If material throughout the early solar system was constantly drifting, mixing, and redistributing itself, why do these two chemical groups remain so clearly separated, even after all this time? Jupiter's early formation offers one compelling explanation. According to this model, Jupiter's growing presence, and the gap it likely carved within the surrounding gas disk, may have acted as a kind of chemical barrier, quite literally separating these two reservoirs of material from one another. Material originating closer to the Sun remained largely confined to the inner solar system. Material originating farther out remained largely confined beyond Jupiter's orbit, with relatively little exchange occurring between the two regions. This barrier appears to have been remarkably effective enough that we can still observe its consequences today, quietly preserved within the chemical signatures of meteorites collected here on Earth. In essence, Jupiter's presence, quite early in the solar system's history, appears to have helped preserve a kind of isotopic memory. A record, still faintly readable within ancient rocks, of just how separated these two regions of the early solar system truly were. This same barrier appears directly connected to what scientists often describe as the carbonaceous versus non-carbonaceous meteorite dichotomy, a division that remains one of the most well-studied and significant chemical patterns observed throughout solar system science. Rather than the inner and outer solar system gradually blending together over time into a single, more homogeneous chemical reservoir, Jupiter's early presence appears to have helped preserve their distinctiveness, keeping these two chemically different regions largely separate from one another throughout the critical early period when planets were still actively forming. Now, it's worth pausing here to note that scientists continue refining exactly how this separation occurred. Some models emphasize Jupiter's overall mass and gravity as the primary reason these two reservoirs remain separated. But other, more recent models suggest something slightly more specific may have been at work. Rather than Jupiter's mass alone creating this barrier, it may have been a particular pressure maximum, a subtle but significant peak in gas pressure, forming specifically near Jupiter's orbit within the disk, that played the truly decisive role in keeping these two chemical reservoirs apart. This distinction matters, because it suggests the separation between these two chemical families was not simply a byproduct of Jupiter's size, but rather, a more specific consequence of exactly where, and how, Jupiter's growth reshaped the pressure and density patterns within the surrounding disk. Either way, one thread remains constant throughout these various models. Jupiter's early growth likely prevented extensive inward drift of pebbles from the outer disk, significantly limiting how much mixing occurred between these two chemically distinct regions of the early solar system. And this preserved separation appears to have had a direct, lasting impact on the very planet we call home. Because Earth, and its smaller, more distant neighbor Mars, appear to have formed largely from this distinct inner solar system reservoir, rather than from some more thoroughly blended combination of inner and outer material. In other words, the very ingredients that came together to form our planet, the specific chemical and isotopic makeup of the rocks beneath our feet, the elements that eventually became part of Earth's oceans, atmosphere, and even, eventually, its living organisms, trace back to this particular, relatively isolated reservoir of inner solar system material. A reservoir that remained largely distinct, thanks in part to Jupiter's quiet, early influence holding the two regions apart. Which brings us, once again, to our familiar and ever-deepening question. What if Jupiter had never formed at all? Without Jupiter's early presence, without that pressure maximum, without the gap it likely carved within the surrounding disk, this careful separation between inner and outer solar system material may never have developed in the first place. Material from the colder, more distant regions may have continued drifting inward largely unimpeded, gradually mixing more thoroughly with material closer to the Sun. In such a scenario, the distribution of volatile compounds, water, various ices, certain organic materials, alongside more refractory, rocky material, across the inner solar system, could have looked quite different from the very beginning. Rather than Earth forming predominantly from a relatively dry, isotopically distinct inner reservoir, our planet might have incorporated a noticeably different mixture of ingredients from the very start. It's a delicate thought to sit with. That something as fundamental as the chemical recipe from which Earth itself was built, the very elements that make up our planet, our oceans, and ultimately, every living thing upon it, may trace back, in part, to one giant planet's quiet, early influence over the flow of material through a young and still forming solar system. As we bring this fifth chapter to a gentle close, we find ourselves standing at the halfway point of our long journey together. Behind us now lies a deep and intricate story. Migration and traffic jams within the disk. Rings echoed across distant young star systems. A narrow, carefully preserved inner disk. And now, a chemical barrier, quietly separating two ancient reservoirs of material, still detectable today within ancient meteorites. Each thread, distinct in its details, yet part of the very same underlying story. Jupiter, forming early, growing rapidly, and in doing so, quietly shaping nearly every aspect of the solar system that would eventually follow. In our next chapter, we will continue this journey even further, moving beyond formation and chemistry, toward Jupiter's role in the more dynamic, sometimes turbulent later history of our solar system, exploring what may have happened after the planets had largely settled into place. For now, let this picture rest gently in your mind. Two ancient reservoirs of material, separated by an invisible boundary near Jupiter's orbit. Two distinct chemical stories, quietly preserved across billions of years. And a planet, our planet, built carefully, patiently, from one particular corner of that vast and ancient disk, as we continue drifting, together, deeper into the long, unfolding story of a solar system shaped by a giant. Our story so far has carried us through rings and traffic jams, through migration and chemical barriers, through two ancient reservoirs of material quietly separated by Jupiter's early growth. As we begin this sixth chapter, let us look more closely at what that separation actually meant for the world we now call home. Because chemistry, in the end, is not simply an abstract pattern recorded in ancient rocks. It is the very foundation of what makes a planet livable. Jupiter's early movements, its growth, its possible migration inward and back out again, appear to have played a meaningful role in shaping how volatile compounds were distributed throughout the inner solar system. Volatiles is simply the term scientists use for substances that vaporize relatively easily, water among the most important of them, along with various other compounds essential to a planet's chemistry and, eventually, its potential for life. In our actual history, Jupiter's presence appears to have influenced where these volatile-rich materials ended up. Some remained concentrated farther out, in the colder outer solar system, where ice could remain stable. Others made their way inward, in more limited quantities, eventually becoming part of the material from which Earth and its neighboring planets formed. Without Jupiter, this particular distribution may have unfolded quite differently. The pathways by which water and other volatile compounds traveled from the outer disk toward the inner solar system depended, in part, on the very barriers and pressure structures that Jupiter's growth helped create. Remove Jupiter from that story, and the delicate balance of how much water, and what other volatile-rich material ultimately arrived in the region where Earth was forming, may have shifted considerably. This brings us back, once more, to the barrier we explored in our last chapter, the chemical divide separating carbonaceous material, more common in the outer solar system, from non-carbonaceous material, more closely associated with the inner regions closer to the Sun. We already know that Jupiter's early growth likely played a central role in preserving this separation. But it is worth pausing here to consider what this filtering effect may have meant, not simply for meteorite chemistry, but for the deeper question of habitability itself. Because the specific building blocks available to the early Earth, the particular combination of rocky, refractory material alongside more limited volatile compounds, arriving from careful, filtered pathways rather than a fully blended mixture, may have shaped the fundamental chemistry from which our planet, and everything that eventually lived upon it, first emerged. It's a subtle thread to follow, but a profound one. The very possibility of oceans, of an atmosphere capable of supporting life, of the particular chemical balance that allowed Earth to become the world it eventually became, may trace back, in some small but meaningful way, to how thoroughly, or how sparingly, material from the outer solar system was permitted to mix inward, past the invisible boundary Jupiter's early growth had helped establish. Had Jupiter never existed, that filtering process may never have occurred in quite the same way. And the particular chemical recipe that eventually allowed Earth to become habitable might have looked meaningfully different from the very beginning. Now, let us return briefly to that phosphorus to nitrogen ratio we touched on earlier, because it offers scientists a particularly precise way of measuring just how effective this separation truly was. By comparing this specific ratio between meteorites originating from the inner solar system and those originating from farther out, researchers can trace, with remarkable precision, how limited the exchange of material between these two regions actually was. And time and again, this evidence points back to the same underlying cause. Jupiter's early growth, quietly but effectively limiting how much material ever crossed from one side of that boundary to the other. This is not simply a single line of evidence pointing toward Jupiter's influence, but rather, one piece within a much larger, remarkably consistent picture. The preserved carbonaceous versus non-carbonaceous dichotomy we discussed earlier. The distinct isotopic signatures still measurable within ancient meteorites today. And now, this particular chemical ratio, all pointing toward the same underlying story. A young Jupiter, forming early, and in doing so, drawing a careful, lasting boundary across the early solar system. Let us now turn towards something a little more specific, something concerning not simply where material remains separated, but when certain solid bodies actually formed. Scientists studying the ages of ancient meteorites have discovered something quite curious. Rather than all the earliest solid material in the solar system forming in one single event, there appears to have been at least two distinct phases of planetesimal formation, separated by a gap of roughly 2 to 3 million years. The very first solid bodies, the earliest planetesimals to form within the solar system, appear to have come together quite rapidly, relatively soon after the Sun itself ignited. But then, curiously, there seems to have been a pause. A period where fewer new planetesimals formed. Followed, later, by a second wave of planetesimal formation, emerging several million years after the first. This delayed second generation is not something scientists would necessarily expect if planetesimals simply formed continuously, at a steady, uninterrupted pace, throughout the early solar system. Instead, this distinct gap suggests something specific happened partway through the process, something that temporarily interrupted planetesimal formation, before conditions eventually allowed a new wave of solid bodies to begin forming once again. Jupiter's early growth offers a compelling explanation for this pattern. As we've already explored, Jupiter's formation likely created significant disturbances within the surrounding disk, gaps, pressure bumps, and ring-like structures, all reshaping how material moved and accumulated throughout the disk. It's entirely possible that this disruption, this reorganization of the disk structure caused directly by Jupiter's rapid early growth, is precisely what triggered this delayed second phase of planetesimal formation. In other words, the first generation of planetesimals may have formed simply through the disk's natural, early evolution, before Jupiter had grown large enough to significantly disturb its surroundings. But once Jupiter reached a certain critical size, carving its gap, creating pressure bumps along the disk structure, an entirely new set of conditions emerged, conditions that encouraged a second wave of solid material to begin accumulating, several million years after the very first planetesimals had already formed. This idea finds further support when scientists examine the specific ages of non-carbonaceous chondrites, a particular category of ancient meteorites originating from the inner solar system. When researchers carefully measure the formation ages of these meteorites, they find a pattern that fits remarkably well with this two-phase model. Rather than all non-carbonaceous chondrites sharing a single, uniform age, their formation times appear to cluster around these same two distinct periods, an earlier phase, and a delayed, later phase, separated by roughly the same 2 to 3 million year gap. This alignment offers scientists a particularly compelling piece of evidence. If Jupiter's growth genuinely triggered this delayed second phase of planetesimal formation, then we would expect to find meteorites whose ages closely match this predicted timeline. And that is precisely what researchers observe when they examine the non-carbonaceous chondrite record in detail. In this way, the very ages recorded within these ancient meteorites, tiny fragments of rock, largely unchanged since the earliest days of the solar system, become quiet historical witnesses, preserving, within their mineral structure, a faint but measurable echo of Jupiter's early growth, and the disruption it likely caused within the surrounding disk, billions of years ago. It is a remarkable thing to consider, that a rock, small enough to hold in your hand, recovered perhaps from a desert or an ice sheet somewhere here on Earth, might carry within it a kind of frozen memory. Not simply of when it formed, but of the broader story unfolding around it. The quiet disruption of a forming Jupiter, rippling outward through the disk, shaping not only where material gathered, but precisely when. And so, once again, we return to our familiar and ever-present question. What if Jupiter had never existed at all? Without Jupiter's early growth, without the disruption it introduced into the surrounding disk, this particular two-phase pattern of planetesimal formation may never have occurred. Instead, planetesimals throughout the solar system may have continued forming along a more continuous, less interrupted timeline, without that distinctive multi-million-year pause between generations. In such a scenario, the meteorite record we observe and study today, here on Earth, might look considerably different. The particular clustering of ages we currently find among non-carbonaceous chondrites, that quiet echo of Jupiter's early disruption, preserved patiently across billions of years, may simply never have existed in the first place. It is a striking thought, that even something as seemingly small and specific as the precise timing pattern recorded within ancient meteorites, might ultimately trace back to the presence, or the absence, of one single giant planet, quietly shaping the story of an entire solar system, from its very earliest days. As we bring this sixth chapter to a close, let us take a moment to notice just how far this story has carried us. From the broad architecture of planetary orbits, down to the most delicate isotopic signatures. From the size of Mars, to the precise timing recorded within individual meteorites. Each thread, distinct in its details, yet part of the very same underlying pattern. A solar system whose entire history appears to be woven, quietly but thoroughly, around the early presence of Jupiter. In our next chapter, we will continue this journey, moving toward Jupiter's role in the later, more dynamic history of the solar system, exploring what happened, not simply during formation, but in the long, eventful ages that followed, as the planets settled, slowly and gradually, into the stable configuration we know today. For now, let this picture rest quietly in your mind. 2 generations of planetesimals, separated by a patient, multi-million-year pause. a careful chemical filtering, shaping the very ingredients from which Earth eventually became habitable. And ancient meteorites, small and quiet, still carrying within them a faint, lasting memory of the giant planet that once reshaped the solar system around them, as we continue drifting, together, deeper into this long and remarkable story. We ended our last chapter with a quiet image, small meteorites, patiently holding within them a faint memory of Jupiter's early disruption, still readable billions of years later. Let us pick up that thread once more, because it leads us somewhere new. Toward a region of the solar system many of us picture as simple leftover rubble, but which, as we'll come to see, tells its own careful story about Jupiter's influence. Before we arrive there, let us linger a little longer on the disk itself, and one more subtle mechanism through which Jupiter shaped the material around it. As Jupiter grew, and as the terrestrial planets themselves began to take shape closer to the Sun, a curious secondary effect appears to have unfolded. The very process of terrestrial accretion, small bodies colliding, merging, and growing into larger embryos, naturally released a certain amount of fine dust back into the surrounding disk. Debris from collisions. Material shed during those early, sometimes violent encounters between forming worlds. Ordinarily, in a disk still rich with gas, this loose dust might simply have drifted, dispersed, or been swept along by the surrounding currents of gas and radiation. But Jupiter's presence had already begun depleting gas from certain regions of the disk, carving its now familiar gap, thinning the surrounding material in ways we've explored throughout this journey. And within these gas-depleted regions, conditions seem to have been particularly favorable for that freshly released dust to settle and begin clumping together once again. Not simply drifting away into nothing, but gathering, slowly, into entirely new planetesimals. It's a rather elegant image, when you sit with it. The debris of one generation of forming worlds, quietly recycled into the seeds of another. And Jupiter, indirectly, gently shaping the very conditions that made that recycling possible. This connects naturally back to the pressure bumps we explored earlier in our story, those regions within the disk where Jupiter's gap-carving influence caused material to slow and accumulate rather than drift steadily inward. We know these pressure bumps likely trapped dust and encouraged the formation of new solid bodies. And we know, too, that this same disruption likely produced the broader ringed structures we can still observe echoed today, in the disks surrounding other young, still forming stars scattered across the galaxy. Each of these threads, the recycled dust from terrestrial accretion, the pressure bumps trapping material in place, the wider ringed architecture stretching across the disk, all point back to the same underlying cause. And each helps explain something we touched on in our last chapter as well, that curious two-phase pattern of planetesimal formation, an early generation, followed by a distinct, delayed second wave, arriving several million years later. Taken together, these processes suggest something rather significant about the solar system's early history. It was not simply a matter of material accumulating steadily, continuously, along one smooth, predictable timeline. Jupiter's growth appears to have introduced genuine pauses, delays, and renewed bursts of activity throughout the disk's evolution, altering not only where planets and planetesimals formed, but precisely when. Had Jupiter never existed, this entire schedule may have unfolded quite differently. Perhaps more gradually. Perhaps more evenly. Without the particular rhythm of disruption and renewal that Jupiter's early presence appears to have introduced into the story. Now, let us turn our attention to a region of the solar system that many of us picture quite simply. A scattered band of rocky rubble, drifting quietly between Mars and Jupiter. The asteroid belt. At first glance, it might seem like a fairly unremarkable place. Leftover debris, never quite gathered into anything more substantial. But the more closely scientists examine this region, the more its story reveals itself to be deeply, intricately connected to Jupiter. One of the most fundamental questions about the asteroid belt is remarkably simple to ask, yet surprisingly complex to answer. Why did the material there never come together to form a proper planet? Jupiter appears to be central to that answer. Positioned just beyond the asteroid belt, Jupiter's immense gravity likely played a significant role in preventing the rocky material within that region from ever settling into the calm, stable orbits necessary for planet formation to proceed normally. Rather than gently drawing material together, Jupiter's gravitational influence tended to excite and disturb the orbits of asteroids within this region, keeping their paths just energetic, just chaotic enough, to prevent the slow, gradual process of accretion from ever fully taking hold. In other words, the asteroid belt may exist, not because there was ever a shortage of material there, but because Jupiter's gravity actively worked against that material ever calmly gathering itself into a single, unified planet. This connects directly back to something we explored earlier, the chaotic excitation that Jupiter and Saturn's early migration likely introduced into the surrounding disk. We discussed how this turbulence helped shape the narrow region where the terrestrial planets ultimately formed, closer to the Sun. But that same turbulent influence extended outward as well, directly affecting the region where the asteroid belt exists today. Jupiter and Saturn, through their combined gravitational interactions, particularly during the more dynamic, migratory phase of their early history, appear to have specifically prevented the asteroid belt from ever accumulating enough mass, or ever remaining stable enough, to form a genuine planet of its own. It's worth pausing here for a moment, to consider just how different our solar system might look today, if that particular dynamic had never unfolded. A fifth rocky world, perhaps, sitting quietly between Mars and Jupiter, rather than the scattered, fragmentary belt of asteroids we observe there instead. This idea also helps explain something else, a puzzle that has intrigued planetary scientists for quite some time. Why the asteroid belt, despite occupying a fairly modest region of space, contains such a surprisingly small amount of total mass. Current estimates suggest that if you gathered every asteroid within the belt together into a single body, it would still amount to only a small fraction of our Moon's mass. Remarkably little, for a region often imagined as a vast, dense field of rubble. Jupiter and Saturn's early interactions appear to offer a compelling explanation for this modest mass as well. Rather than simply preventing the material from forming a planet, their combined gravitational influence likely scattered a significant portion of that material away entirely. Flinging asteroids into more distant orbits, ejecting some from the solar system altogether, or sending others spiraling inward, eventually colliding with the young terrestrial planets still forming closer to the Sun. In this sense, Jupiter and Saturn were not simply passive bystanders, quietly observing a planet that never quite managed to form nearby. They were, in a very real sense, actively responsible for keeping the asteroid belt small, for scattering away much of what might otherwise have remained there. There is something quietly fascinating in learning that the asteroid belt's most defining characteristic, its surprisingly modest total mass, is not simply an accident of leftover material, but a direct, measurable consequence of Jupiter and Saturn's early gravitational relationship with one another. And this leads us toward an even more specific and elegant piece of the story, one involving a particular kind of gravitational relationship between Jupiter and Saturn. In certain models describing the early solar system, Jupiter and Saturn's orbits may have passed through a phase where they existed in what scientists call a near-resonant configuration. Meaning, their orbital periods around the Sun fell into a particular, near-whole number ratio relative to one another. A relationship that can create especially strong, especially rhythmic gravitational interactions between two orbiting bodies. This particular near-resonant relationship between Jupiter and Saturn appears to have had a profound effect, not simply on the asteroid belt's total mass, but on its detailed internal structure as well. Scientists studying the asteroid belt today notice something quite interesting. It is not simply a uniform scattering of similar objects. Instead, it contains a genuinely mixed population, different taxonomic types of asteroids, distinguished by their composition and reflective properties, often found intermixed with one another throughout the belt, rather than neatly separated by distance from the Sun. This particular near-resonant configuration between Jupiter and Saturn may help explain that mixed population. As the two giant planets move through this specific gravitational relationship, their combined influence likely stirred and redistributed asteroids throughout the belt in a particularly effective and thorough way. Scattering material inward and outward in complex, overlapping patterns, ultimately producing the intricate, somewhat jumbled orbital structure and mixed compositional variety that we continue to observe within the asteroid belt today. Finally, this same dynamic appears connected to Jupiter's broader migration history throughout the early solar system. The same migration we explored earlier in our story, the grand tack, Jupiter moving inward before eventually retreating back outward. That migration was not simply a passive backdrop to the asteroid belt story. It appears to have directly contributed to shaping the belt's particular orbital architecture. Not merely determining how much total mass remained within the region, but actively influencing precisely how that remaining material became arranged, scattered, and distributed throughout the belt's characteristic orbital patterns. In other words, the very structure of the asteroid belt we observe today, its overall shape, its mixed variety of asteroid types, its particular pattern of orbital distances, may trace back quite specifically to the precise details of Jupiter's early migration. Not simply Jupiter's presence in general, but the specific path it followed, and the specific timing with which it moved inward, and then back outward again. As we bring this seventh chapter to a gentle close, it becomes clear that the asteroid belt, so often imagined as simple leftover debris, quietly drifting between Mars and Jupiter, is in fact a remarkably detailed historical record. A patient, scattered archive, preserving within its structure, its mass, and its mixed composition, a faithful record of Jupiter's earliest movements through the young solar system. Had Jupiter never existed, this region may have told an entirely different story. Perhaps a fifth rocky planet, quietly orbiting where the asteroid belt exists today. Or perhaps something else entirely, shaped by whatever different gravitational relationships might have unfolded in Jupiter's absence. In our next chapter, we will continue this journey, moving further still into Jupiter's long, complex relationship with the solar system's small bodies, exploring what came next, as the planets, at last, began settling into the stable, enduring architecture we recognize today. For now, let this picture rest quietly in your mind. A gentle band of scattered stone, drifting patiently between Mars and Jupiter, not empty leftover space, but a careful, ancient record, still faintly echoing the particular rhythm of Jupiter's earliest journey through our solar system, as we continue drifting, together, deeper into this long and remarkable story. Our last chapter left us with the asteroid belt itself, scattered and patient, quietly recording Jupiter's earliest movements through the young solar system. Now let us look more closely at what that record actually contains. Because the belt is not simply shaped by where material ended up. It is shaped, just as deeply, by the violent, turbulent history it endured along the way. If Jupiter had never existed, the asteroid belt we know today would likely be a very different place. Not simply in terms of how many rocky bodies it contained, though that number would almost certainly differ as well, but in something more fundamental. How those bodies are dynamically organized. The particular pattern of orbits, resonances, and groupings that gives the belt its intricate internal structure would likely never have formed in quite the same way. This distinction matters. It would be easy to imagine an asteroid belt without Jupiter as simply a larger, more crowded version of the one we observe today. More rocks, perhaps, left undisturbed, never scattered or ejected. But the reality appears more nuanced than that. Jupiter's influence did not simply reduce the belt's total mass. It fundamentally shaped the belt's internal architecture, the specific way its remaining material settled into distinct families, resonant gaps, and orbital groupings. Without that shaping influence, the region between Mars and the outer solar system might have organized itself according to an entirely different set of rules. Some models even suggest something rather curious about what might happen to the asteroid belt over very long timescales, in a solar system without Jupiter. Rather than remaining calm and stable indefinitely, the belt may actually become increasingly unstable as time passes. Gradually, many of its bodies could begin to wobble away from their original paths, drifting into new, less predictable orbits. This is a subtle but important point. Jupiter's gravity, while clearly responsible for much of the early disruption we've already discussed, may also play an ongoing, stabilizing role today, helping to maintain certain regularities within the belt's current structure. Remove that steady, continuous influence, and the careful order we now observe within the asteroid belt might slowly begin to unravel over extremely long stretches of time. It's a reminder that Jupiter's relationship with the asteroid belt was never simply a single event confined to the ancient past. It appears to be an ongoing relationship, one that continues shaping the belt's structure even now, quietly, patiently, across billions of years. Let us turn now toward the deeper, more violent chapter of this story, a period some researchers have given a rather evocative name. Some studies describe Jupiter's early dynamical disturbance within the asteroid belt region using a term that echoes another, more familiar chapter of solar system history. They call it the Jovian early bombardment. A period, early in the solar system's history, when Jupiter's growing gravitational influence appears to have stirred up planetesimals throughout the asteroid belt region with particular intensity. This term deliberately calls to mind the more widely known late heavy bombardment, a period when the inner solar system, including the Moon and Earth itself, is thought to have experienced a surge of impacts from wandering debris. But this Jovian early bombardment describes something different. An earlier, more localized period of intense disturbance, centered specifically around the asteroid belt, and driven directly by Jupiter's own growth and gravitational reach. As Jupiter grew large enough to significantly influence the surrounding disk, its gravity appears to have destabilized portions of the nearby planetesimal population. Rather than a gentle, gradual settling into calm orbits, this region likely experienced a genuinely turbulent period, an intense stretch of gravitational stirring, where countless small bodies found their orbits abruptly and repeatedly disturbed. To understand why this happens so specifically within certain regions, it helps to consider something scientists refer to as orbital resonance. When a smaller body's orbital period falls into a simple, whole number ratio relationship with a much larger body's orbit, their gravitational interaction becomes especially strong and repetitive. Rather than a single, gentle nudge, the smaller body experiences the same particular gravitational tug, again and again, at predictable points along its orbit, gradually building up a much larger cumulative effect over time. As Proto-Jupiter grew, it appears to have significantly increased what scientists call encounter velocities, essentially, the relative speed at which planetesimals within these resonant regions passed by, or collided with, one another. Faster, more energetic encounters make it considerably harder for smaller bodies to gently merge and grow into larger ones. Instead of the slow, careful accretion needed to build a planet, these resonant regions became genuinely hostile environments, more prone to destructive collisions than gentle, planet-building mergers. One particular resonance appears to have played an especially significant role in this story, a relationship where a smaller body's orbital period was almost exactly half that of Jupiter's own orbit, a pattern scientists refer to as the 2-to-1 resonance. Within this specific resonant region, Jupiter's influence appears to have been especially disruptive. Planetesimals caught within this particular orbital relationship experience dramatically increased gravitational stirring, making it especially difficult for material there to grow into anything larger. Rather than becoming a nursery for new, larger bodies, this region instead became a particularly active, particularly turbulent zone, where growth was actively suppressed rather than encouraged. This disruption appears connected directly to Jupiter's broader migration story as well, the same inward and outward movement we've explored several times throughout our journey together. As Jupiter migrated through the early solar system, its shifting position appears to have swept various planetesimals into these disruptive resonant relationships, sometimes described as entraining them, drawing kilometer-scale planetesimals, bodies roughly a few kilometers across, into these particularly active resonance zones. Once caught within these resonances, these planetesimals experienced a dramatic increase in what scientists call orbital eccentricity, essentially, how elongated and irregular their orbital paths became, rather than remaining calm and nearly circular. This increased eccentricity meant these bodies began crossing paths with one another far more frequently, and far more violently, than they otherwise would have. The consequences of this were significant, and rather dramatic when you picture it clearly. Rather than gently merging together, as planetesimals often do under calmer conditions, these excited, high-speed bodies increasingly collided with tremendous force. Rather than building larger structures, these violent impacts instead broke larger bodies apart, shattering them into smaller and smaller fragments. Scientists describe this process using a particularly evocative term, a collisional cascade. Picture it almost like a chain reaction, moving in the opposite direction from what we might expect during normal planet formation. Rather than small pieces gradually building into larger ones, larger bodies instead break down into progressively smaller and smaller pieces, cascading downward in size, collision after collision, fragment after fragment. Jupiter's migration, through this particular mechanism, appears to have triggered exactly this kind of destructive cascade within the surrounding planetesimal population, grinding down what might otherwise have become larger planetary building blocks into countless smaller, fragmented pieces instead. And this final piece of the story carries one more surprising consequence, connecting this violent, fragmenting process to something happening much closer to the Sun. As this collisional cascade proceeded, grinding larger planetesimals into progressively smaller pieces, these smaller fragments became increasingly susceptible to something called gas drag, a subtle but persistent force, caused by their movement through the still-present gas within the surrounding disk. Unlike larger bodies, which move through this gas with relatively little resistance, smaller fragments experience considerably more drag, gradually losing orbital energy and slowly spiraling inward over time. Remarkably, this process may have had consequences reaching all the way to the inner solar system. Some models suggest that this gas drag, acting upon smaller planetesimals produced by Jupiter's disruptive influence within the resonance regions, may have driven certain pre-existing short-period planets, worlds that may have already formed closer to the Sun, to spiral inward even further, eventually being consumed by the Sun entirely. It's a striking thought to sit with, that Jupiter's disruption of a relatively distant region, the area we now recognize as the asteroid belt, may have set into motion a chain of consequences reaching all the way inward, quietly influencing the fate of planets forming much closer to the Sun. As we bring this 8th chapter to a gentle close, we find ourselves holding a rather different picture of the asteroid belt than the one we perhaps began with. Not simply a quiet region of leftover rubble, patiently drifting between Mars and Jupiter, but the scarred, fragmented remnant of a genuinely violent period, an early bombardment, a collisional cascade, an entire population of planetesimals ground down, scattered, and reshaped by Jupiter's early, restless growth. In our next chapter, we will continue following these threads even further, moving toward the long, gradual settling of the solar system into the stable configuration we recognize today, and toward the final, deeper question our journey has been slowly building toward all along. For now, let this picture rest quietly in your mind. A distant region, once softly gathering into what might have become a planet, instead ground slowly into fragments by Jupiter's early, restless growth, small pieces, drifting gently inward, carrying with them the last quiet echoes of worlds that, in this particular telling of our solar system's story, never quite had the chance to fully form. We ended our last chapter with fragments drifting quietly inward, the last remnants of worlds that never quite formed. Now let us follow those fragments a little further, into a question many of us have wondered about at some point, whether idly gazing up at the night sky, or hearing it mentioned in passing. Does Jupiter actually protect Earth? For a long time, this idea held a comfortable, almost mythic status in popular science. Jupiter, the great celestial shield, quietly standing guard at the edge of the inner solar system, catching or deflecting dangerous comets before they ever have the chance to threaten Earth. It's a comforting image. But as we look more closely, the reality reveals itself to be considerably more layered, more nuanced, than that simple picture suggests. Let us begin with the part of this idea that does appear to hold up reasonably well, at least in certain respects. Jupiter's immense gravity does appear to play a meaningful role in deflecting or ejecting long-period comets, wandering icy bodies that occasionally drift in from the very distant outer reaches of the solar system, sometimes from a vast, distant region known as the Oort cloud. As these comets fall inward, their long, elongated orbits sometimes carry them close to Jupiter's own path. When this happens, Jupiter's powerful gravity can dramatically alter their trajectory, sometimes flinging them outward into much more distant orbits, sometimes ejecting them from the solar system entirely. In this particular sense, Jupiter does appear to reduce the overall number of long-period comets that might otherwise continue drifting inward toward Earth. Without Jupiter's presence, Earth would likely face a somewhat higher frequency of encounters with these particular wandering visitors from the outer solar system. This connects to a broader idea scientists sometimes describe as gravitational sweeping. Throughout the solar system's long history, Jupiter's gravity has continuously interacted with countless small bodies, asteroids and comets alike, gradually clearing certain regions, and redirecting material away from paths that might otherwise cross Earth's own orbit. Without Jupiter, many of these sweeping effects would simply never have occurred. A greater number of small bodies might remain on orbits that periodically cross Earth's own path through space, rather than being redirected elsewhere, or removed from the inner solar system entirely, as they have been throughout Jupiter's long presence. There is a subtler consequence connected to this idea as well, one involving not simply how many comets exist, but where they tend to accumulate over time. In a solar system without Jupiter's continuous gravitational influence, certain distant comet reservoirs, regions where countless icy bodies slowly drift and accumulate over billions of years, may become considerably more densely populated than they are in our actual solar system. Without Jupiter periodically scattering, ejecting, or redirecting material away from these regions, more comets may simply remain there, gradually building up in greater numbers over time. This shift would not simply mean more comets waiting somewhere out in the distant solar system. It would mean an entirely different long-term storage and evolution pattern for cometary material throughout the solar system's history, changing not just the total quantity of comets present, but the very structure and behavior of the reservoirs where they reside. This connects to another important piece of Jupiter's influence, its remarkable ability to fling objects entirely out of the solar system. Jupiter's mass is so significant that it remains one of the very few bodies within the solar system capable of delivering a strong enough gravitational kick to send passing comets or asteroids permanently out of the Sun's gravitational influence altogether, sending them drifting into interstellar space, never to return. Without Jupiter, considerably fewer objects would likely receive this kind of powerful ejection. Rather than being removed from the solar system entirely, more comets and asteroids may simply continue circulating internally, drifting along various paths through the solar system over extremely long stretches of time, rather than eventually departing altogether. Now, here's where the story becomes considerably more interesting, and where that simple, comforting image of Jupiter the protective shield begins to reveal a more complicated reality. Because Jupiter's gravity does not only push objects away from the inner solar system. In certain circumstances, it can just as easily nudge them inward instead. Some scientific studies suggest that rather than functioning as a simple, universal shield, Jupiter's gravitational influence may, in certain situations, actually increase the number of asteroids and short-period comets that end up on Earth-crossing orbits. Rather than always deflecting dangerous objects away, Jupiter's gravity can sometimes redirect material from more distant, stable regions, nudging it inward, onto orbital paths that eventually bring it closer to Earth than it might otherwise have traveled. This is a genuinely important nuance, one that has shifted scientific understanding considerably in more recent years. Jupiter's relationship with Earth's impact history is not simply protective. It is more accurately described as redistributive, sometimes reducing certain types of impact risk, while simultaneously increasing others. This redistributive influence becomes particularly clear when we consider the population of what scientists call near-Earth asteroids, relatively small bodies whose orbits bring them into proximity with Earth's own path around the Sun. Many of these near-Earth asteroids originate from the main asteroid belt, gradually migrating outward from their original orbits due to a combination of subtle forces and gravitational interactions, including, quite significantly, interactions with Jupiter itself. Jupiter's gravity plays a meaningful role in both creating, and subsequently redirecting, certain asteroids from the main belt onto new orbital paths, some of which eventually become Earth-crossing. Without Jupiter, this particular replenishment process, asteroids migrating from the main belt into near-Earth space, would likely occur quite differently. Some models suggest that without Jupiter's ongoing gravitational influence, considerably fewer new near-Earth objects may form over long periods of time, since one of the solar system's primary mechanisms of orbital scattering, the very process that helps redirect asteroids from the main belt into Earth-crossing orbits in the first place, would simply no longer exist in the same way. Taken together, all of these threads point towards something more subtle, and honestly, more scientifically interesting, than the simple protective shield narrative many of us grew up hearing. Without Jupiter, the inner solar system would not simply experience either more or fewer impacts than it does today. It would likely experience an entirely different population of impacting objects altogether. Different source regions, different orbital histories, a different balance between long-period comets, short-period comets, and near-Earth asteroids, each shaped by an entirely different set of gravitational relationships than the ones that have actually governed our solar system's history. In other words, the question is not simply, would Earth be safer or more dangerous without Jupiter? The more accurate question is, what kind of danger would Earth face instead? A different mixture, a different rhythm, a different long-term story of impacts, written across a solar system organized along entirely different gravitational lines. Now, let us turn toward one final, particularly significant thread within this part of our story. One that touches not simply on danger, but on something far more essential to Earth's own story. Water. For a long time, scientists have wondered exactly how Earth acquired its water. Our planet formed, according to most models, in a relatively warm region of the early solar system, likely too warm for large quantities of water ice to have condensed directly from the surrounding disk material during Earth's initial formation. This has led many researchers to believe that at least a significant portion of Earth's water arrived later, delivered from farther out in the solar system, carried inward by icy bodies, comets, and certain types of asteroids, over the course of Earth's early history. And once again, Jupiter's early presence appears deeply connected to this story. Some research suggests that Earth's water delivery may have depended quite specifically on transport pathways established by Jupiter and Saturn, particularly during the solar system's first 10 to 20 million years, a relatively narrow, critical window early in our planet's formation. During this period, Jupiter and Saturn's combined gravitational influence appears to have played a meaningful role in redirecting certain water-rich icy bodies, originally located much farther out in the solar system, inward toward the region where Earth was still actively forming. Rather than remaining permanently isolated in the distant outer solar system, some fraction of this ice-rich material was gravitationally nudged inward, eventually contributing to Earth's growing supply of water during this critical formative period. Without Jupiter's presence, this particular delivery pathway may never have existed in the same way. The specific gravitational relationships between Jupiter, Saturn, and the surrounding disk, relationships that appear to have helped guide water-rich material toward the inner solar system, would simply not have unfolded in the same manner. In such a scenario, some research suggests that Earth may have ended up considerably drier than it actually is today. Not necessarily devoid of water entirely, other delivery mechanisms may still have contributed some water over time, but potentially lacking the particular abundance of surface water, oceans, and hydrological cycles that have played such a defining role throughout Earth's long history. It's a profound thought to sit with, quietly, for a moment. That the oceans stretching endlessly across our planet's surface, the very water flowing through rivers, and clouds, and rain, water so fundamental to life itself, may trace back, in some meaningful part, to a very particular, very specific gravitational relationship between Jupiter and Saturn, unfolding quietly during the earliest years of our solar system's history. As we bring this 9th chapter to a gentle close, we find ourselves holding a far more layered picture of Jupiter's relationship with Earth than perhaps we began with. Not simply a protective giant, standing quietly guard at the edge of the inner solar system, but something more complex. A redistributor of danger, in some ways more protective, in other ways less so, than the simple stories often suggest. And, quite remarkably, perhaps one of the essential architects behind the very water that fills our oceans today. In our next, and final, chapter, we will draw all of these long, intricate threads together. From formation to migration, from chemistry to comets, from the size of Mars to the water in Earth's oceans. And we will sit, together, with the full and complete shape of this question we've been carrying with us throughout this entire journey. What would our solar system, and our own world, truly look like, if Jupiter had never existed at all? For now, let this picture rest quietly in your mind. A giant planet, neither simple guardian nor simple threat, but something more intricate, more woven into the fabric of our world than we might have first imagined, quietly shaping not only the dangers Earth has faced throughout its long history, but the very water that fills its oceans, as we drift, together, toward the final chapter of this long and remarkable story. This is our final chapter. 90 chapters worth of quiet reasoning have carried us here, through migration and dust traps, through chemical barriers and shattered planetesimals, through comets nudged both inward and away. Now, at last, we arrive at the deepest layer of this question, the layer where formation and fate quietly become the same story. Let us begin with something Earth carries within it every single day, almost invisibly. Its orbit. Earth's path around the Sun feels, to us, permanent. Fixed. A gentle, unchanging ellipse, traced faithfully year after year, for as long as human beings have existed to notice it. But over extremely long timescales, millions and hundreds of millions of years, orbital stability is not simply guaranteed. It depends on a delicate, ongoing balance among all the gravitational relationships within the solar system. Jupiter, by virtue of its enormous mass, plays a meaningful role in maintaining that long-term balance. Its gravity helps regulate certain resonant effects among the inner planets, subtly reinforcing the kind of long-term stability that allows Earth's orbit to remain, for practical purposes, remarkably steady across immense stretches of time. Without Jupiter's presence, some models suggest that Earth's orbit could have been considerably less stable over these long timescales. Rather than remaining fixed within its familiar, comfortable range, Earth's distance from the Sun could have gradually drifted, perhaps edging closer over time, perhaps drawing farther away, shifting the delicate thermal balance that has allowed liquid water, and everything that depends upon it, to persist so reliably across billions of years. It's worth noticing, here, that this isn't only a question of distance. Jupiter's gravity also influences something a little more subtle, the orbital planes of the other planets, the particular tilt and alignment along which each world travels around the Sun. Without Jupiter, this geometry, the precise angles at which the planets' orbits are inclined relative to one another, would likely have settled differently as well. Not simply closer or farther from the Sun, but arranged along a different set of orbital planes altogether. A subtly different architecture, still stable perhaps, but genuinely distinct from the one our solar system actually developed. This leads us back, once more, to the earliest and most turbulent period of all, the era of planetary formation itself, when Earth was not yet a finished world, but still a chaotic gathering of colliding embryos and fragments. We've already explored, throughout this journey, several ways in which Jupiter's gravity helped calm certain regions of the early disk, helped narrow the zone where terrestrial planets formed, helped limit how much additional material continued arriving from farther out. Each of these effects, in its own way, contributed to lowering the overall level of chaos during Earth's formation. Without Jupiter, the chances of catastrophic collisions during this critical period would likely have been higher. More crowded material, more competing embryos, more opportunities for violent, disruptive impacts, rather than the relatively more orderly accumulation that ultimately shaped Earth as we know it. And this connects to something particularly significant in Earth's own story, the very event that gave us our moon. According to the leading scientific model, the moon formed following an enormous collision, sometimes called a giant impact, between the young Earth and another large, planet-sized body. This was not a minor event. It was one of the most transformative moments in our planet's entire history, an encounter violent enough to melt much of Earth's surface, and eject enough material into orbit to eventually coalesce into the moon we see in our sky each night. Interestingly, current models suggest this giant impact likely occurred relatively late in Earth's formation, somewhere between roughly 30 and 55 million years after the solar system's terrestrial planets first began forming. And Jupiter's influence on the surrounding disk's architecture appears connected to that particular timing. By shaping when and how material became available within the inner solar system, limiting certain flows, encouraging others, Jupiter's presence appears to have contributed to the specific pacing of terrestrial planet growth, including, indirectly, the timing of this pivotal, moon-forming collision. Without Jupiter, this timing could easily have unfolded differently. Perhaps earlier. Perhaps later. Perhaps, in certain scenarios, not quite the same event at all. And since the moon itself plays a meaningful role in stabilizing Earth's axial tilt, a role connected to Earth's long-term climate stability, this single shift in timing carries consequences reaching far beyond the moment of impact itself. Now, it's important, as we near the end of this long journey, to hold on to something we've touched on more than once throughout this story. Jupiter's influence was never simply, purely destructive. In certain scenarios, models suggest that Jupiter's inward migration, the same grand tack journey we've followed since our very first chapter together, may have actually lowered what scientists call random velocities among planetesimals near Earth's orbit, roughly 1 astronomical unit from the Sun. Lower random velocities mean gentler, calmer relative motion among nearby bodies, conditions that can, in certain cases, actually make it easier for rocky material to merge together smoothly, rather than colliding destructively. In other words, in at least some scenarios, Jupiter's passage through the inner solar system may have helped organize and calm the surrounding material, damping down some of the chaotic motion, and creating, in certain windows of time, conditions genuinely more favorable for efficient planetary growth. This is an important nuance to sit with, gently, as we bring this long story toward its close. Jupiter's story, throughout our entire journey together, has never been a simple tale of protection versus destruction, of shield versus threat. It has been something far more layered. A story of construction and disruption intertwined. Of chemistry reorganized. Of timing reshaped. Of material sometimes swept away, and sometimes gently gathered into place. Which brings us, finally, to the deepest question this entire journey has been quietly circling all along. Would Earth exist at all, in anything resembling its current form, if Jupiter had never been present to help shape the solar system around it? Based on everything we've explored together, across every one of these 100 quiet facts, the most honest answer seems to be this. Almost certainly not. Not in this particular form. Not with this particular size, this particular chemistry, this particular moon, orbiting at this particular distance from the sun, carrying water across this particular proportion of its surface. And if Earth itself would likely have been different, then the deeper question of life follows naturally behind it. Life on Earth, in the specific form we know it, may never have developed in quite the same way, or perhaps at all, in a solar system shaped by harsher, more frequent impacts, by a less stable orbit, by a different distribution of water and volatile material across the inner planets. The particular calm that allowed billions of years of relatively steady, uninterrupted conditions patient enough to allow single cells to slowly become forests, and oceans, and eventually, minds capable of asking questions like the one we've spent this entire journey exploring together, may itself trace back, in some quiet but essential way, to Jupiter's ancient presence in the outer solar system. Because when we step back now, and look at the full shape of everything we've gathered across this long journey together, one thread runs consistently through all of it. Jupiter's role in our solar system's story was never only about protection, deflecting comets, shielding Earth from danger. It was, just as fundamentally, about construction. About redistribution. About the careful, patient reorganizing of chemistry, dust, and timing throughout the young solar system's earliest, most formative years. Jupiter shaped where material gathered, and where it remained scarce. It shaped when planets formed, and how quickly. It shaped which chemical ingredients Earth ultimately received, and which it did not. It shaped the size of Mars, the modest scale of our terrestrial planets, the very existence of the asteroid belt drifting quietly between Mars and the outer solar system. And it shaped, too, the timing of the moon's formation, and the delicate, long-term stability that has allowed Earth's climate, and Earth's life, to persist so remarkably, across so many hundreds of millions of years. In the end, this was never truly a story about a distant, giant planet, existing in isolation, far out at the edge of our awareness. It was always a story about connection. About how one enormous world, forming quietly in the darkness beyond Mars, billions of years ago, became quietly, deeply woven into the story of every single thing that followed. Including, perhaps most remarkably of all, us. So as this long journey together finally draws to its close, let this final, gentle thought settle over you completely. Somewhere out there, right now, roughly 600 million kilometers away, Jupiter continues its slow, patient orbit around the Sun, just as it has for over 4.5 billion years. Quiet, distant, unassuming in its own way. And yet, woven so completely into the story of our world, that without it, without its early growth, its migration, its gravity reaching outward and inward across the young solar system, the very ground beneath you, the air around you, the water within you, may never have come to exist in anything resembling the form we know today. Thank you for spending these quiet hours with this long, unfolding story. Let this final thought carry you gently now, toward rest, toward sleep, toward the same deep, patient stillness that has allowed our solar system, our Earth, and every living thing upon it, to quietly, patiently come into being, across 4.5 billion years of dark, unfolding time.